Sequences and series may be geometric, which means that each term is created by the multiplication of a common ratio r. In the first couple exercises, we'll determine whether we have a geometric or arithmetic sequence. For geometric, we'll look for the common ratio r. For arithmetic, like we see in this problem, we want to see that there's a common difference d. And remember that arithmetic is a type of linear sequence because of the first constant difference. In the next sequence, which is simply a list of terms, we find that there is no common difference to get from 5 to 1 and then from 1 to 0.2. So now I'll look for common ratios, or in other words, what do I multiply 5 by to get to 1, from 1 to 0.2, and so on. And if it's the same constant ratio r, then we're looking at a geometric sequence. We find that we are repeatedly multiplying by 1/5 to generate the terms of the sequence. The formula of r equaling any term in the sequence divided by its previous term is a way that you can calculate r. As seen here, I chose the third and second term, and then to simplify that without a calculator, I multiplied the numerator and denominator by 10, and then simplified that fraction to find the same result as seen here. This formula for the ratio is useful because you won't always be able to eyeball how to generate the ratio by looking at what you multiply from one term to get to the next. Now that we've determined that r equals 1/5, this is a geometric sequence. And you should get the inkling that geometric behaves like exponential, which is correct because there is repeated multiplication. That brings us to the nth term formula for a geometric series, or sequence rather. Here we see that the nth term is going to equal the first term a sub 1 times r raised to the n minus 1 power. The reason why it's the exponent of n minus 1 is because you don't need an r to generate the first term. It's already there. But then after the first term, that's when you start accumulating the repeated multiplications by r. This formula should remind you of the formulas for exponential growth and decay. In the first example, we want to find the 7th term. So that is n equals 7. This is the first term. And we could find the common ratio r as 4 through inspection visually. And for practice, I also showed here how you would find r by taking any term in the sequence and dividing it by its previous term. To then forecast out to the 7th term, we'll use this formula for a sub 7. Substitute in corresponding values. Always make sure to make your subscripts match. So this subscript of n is significant because it will be the same number over here. So that will help you set up your formulas correctly. Simplifying gives the following answer. You could either put this all into a calculator or, using the order of operations, exponents before multiplication for a final answer of 12,288 using the nth term formula. What if you're asked to find the 7th term when you're not given the first term? You can hijack the formula and make sure that the subscripts match the given subscripts in the problem like follows. I rewrote the original using colors so that the n subscripts match up with the exponent here, and then this one subscript matches with that superscript. And now I'll modify them so that they use the subscripts in the problem. Which makes sense because if I'm starting at the 3rd term, then I only need 5 minus 3 r's to get to the 5th term because I'll have a sub 3 times r to get to the 4th term, and then the 4th term times r to get to the 5th term, or 2 r's multiplied together. Substituting in, we get the following equation. Divide both sides by 36. Solve for r by taking the positive and negative square root of both sides. In geometric problems, you'll often find that it has two common ratio r's, a positive and a negative. Make sure to account for both of them. So when we find a sub 7, we'll have to consider it with r positive, and we'll have to come up with the answer for when r is negative. Hijacking the formula again, we see that I don't need to go back and find the first term. I'm just going to modify the formula to match a subscript of a term that I have, and then set it equal to the subscript of the term that I want. Substituting in, we get the following answer. That gives a sub 7 when r is equal to 3. Now, I don't know if r was originally supposed to be 3 or negative 3, but in mathematics you have to find all possible answers given the clues or the puzzle pieces that you have. So now we'll proceed to then use r is equal to negative 3. Here I chose to use a sub 3 as my starter, just to emphasize that as long as the subscripts match, the formula will work out to the right answer. Even if I swap these two, if I change this order, everything will consistently come up with the correct answer. Notice that the exponent of r is positive, so then this will net positive since it's a negative raised to an even, which will match up with that answer, so I don't need to finish. What I have boxed is the correct answer for the 7th term in this problem. That won't always be the case, so you must always check. Geometric means are terms between any two non-consecutive terms of a geometric sequence. Now there's a special case when there's exactly one term between them. You have this following formula that you need to commit to memory. So here in this problem, we are asked to find the geometric mean of these two terms. The assumption then is that there is exactly one term missing between them. So we use this formula. After fixing the arithmetic mistakes, you come up with this answer. You could just use a calculator, or you could simplify it as you go, like you see here. But now let's verify this. We could set up the following 3 spaces to show that 4/9 and 25/36 is divided with one term in between, and then we could use the nth term formula for a geometric sequence in order to deduce the r value for us and then use it to come up with this answer. And that's a good plan B if you don't remember this formula. So we set up the following spaces, knowing that what's implied with a geometric mean is that there is one unknown in between the given pair of values. There's our nth term formula. We have a sub 1 and a sub 3. There are 3 total terms. And now we could substitute into the formula to find r. But notice here, I'm only taking the principal square root, so only the positive square root, because in the formula, when it's just telling us to find the geometric mean, it's assuming that r is going to be positive. We now use this r value, multiplying a sub 1, to find the geometric mean of these two numbers. Multiplying 4/9 by 5/4, the r value. These simplify, and you get the answer all the same. So remember this approach for geometric mean problems. If you forget this formula, taking only the principal root, and recalling that what is being implied here for geometric mean is that there's only one missing term in between the given two. Now, geometric series meaning sum of the terms with a common ratio r. Here's the formula. S sub n, for n terms, the sum will be defined as, in the numerator, the first term times the difference of 1 and the ratio r to the nth power divided by 1 minus r. So you could tell that this formula goes with geometric because it has r in it. So find the indicated sum for each geometric series. You have to pay attention to the details. This subscripted 8 tells you that you want the sum for the first 8 terms, and it's letting you know that it's geometric, and we'll verify that by visually inspecting and seeing that there is a common ratio R of 2, and 1 is the first term. Using this information in the formula, we get that, and fixing my mistake that n is equal to the subscript here of 8. Now you have to be very careful when you put this into a calculator. It would look like the following. Noting that you need to put parentheses around the denominator after you divide. Simplified, you get the following answer. This problem gave us the sequence expanded out. Sometimes it might be summarized using sigma notation. This is the capital Greek letter for S, which means sum for series. And so what you need to do is pick out the corresponding parts using this model. And this is true when k starts at 1, when your index of summation starts at 1. So right here we could deduce the following information. The top number is n, equaling 6. The first term is implied here to be 1. And then the base, which is the repeated multiplication, because it has the exponent, is an r value of 1/2. Substitute that into the formula. Put it into the calculator, remembering to put parentheses around the denominator, giving the following answer. Or simplifying by hand, dividing by 1/2, you multiply by the reciprocal of 2, and the difference here would be 64 and 64 to make common denominators, and then 64 minus 1 gives that numerator of 63, and then simplify before you multiply, and you get this final answer.